Brasil.
Bem, vou dar início então a esse curso de difusão, né, da professora Irina Starikova, né, uns aspectos práticos da matemática. E maybe I should speak in English. Irina doesn't speak Portuguese very well.
Eu falo pouco português, pouco.
And Irina is from Siberia, from Russia.
Siberia is not another country.
And she studied in Novosibirsk and studied mathematics. And then she did her PhD in University of Bristol in philosophy of mathematics. And presently she is a postdoctorate here in the philosophy department at the University of São Paulo. So let's start the course, and thank you for coming.
Thank you so much. Well, as I said, I'm really grateful that you came today in this horrible weather. This is not my first lecture in Brazil, actually. Professor Osvaldo Pessoa has organized a conference last year where I gave a talk on mathematical beauty, but this is my first time teaching in Brazil. However, so it's a little bit like an experiment in a sense, yes. However, this is exactly not what I'm going to do. I'm not going to teach. I'm not going to have exams, as you know, and test your attendance and knowledge. It's more like a work in progress seminar and work in progress discussion. And I hope so much that in this informal atmosphere we can benefit from our discussion, that we have interactive lectures, not really lectures, interactive meetings, and I will show my research with you, and you will show hopefully your thoughts, your ideas about what I'm saying, right? And I decided that I'm not going to present some information which you can get from books and literature, but I will share with you what I know the best, my research, my findings, right? So it's more like a work in progress, and I'm looking forward for your feedback, of course. The more the better. So let me start with my lecture. Some aspects of philosophy of mathematics, so there are really some aspects. And today is the lecture one. So the central topics of my course are three topics. There are actually two papers I have written so far, and I'm still kind of polishing them, which I want to present. And I think this is what I know, this is what I can share with you, right? So the first one is about mathematical visualizations and thought experiments. Well, mathematical visualizations, I mean diagrams, use of diagrams, graphs, everything you can visualize in mathematics. And their counterparts, thought experiments. I think it's a very interesting topic because experimenting is usually what you can find in sciences and physics, right? But mathematics is such an abstract area of human knowledge. How is it possible to have thought experiments in mathematics? Or somebody could say mathematics is all about thought experiments, experimenting in your mind, yeah, in your imagination. So this is my first paper. And then the second one is mathematical beauty. I think it's also a very puzzling topic because, well, everybody knows what a beautiful girl is, yeah, what a beautiful dress is, but what is a beautiful proof? That's kind of an interesting question, yeah. So these two papers, I want to present you in, I will try to be as clear as possible, and they are not just armchair philosophy papers, they are case studies. So I am using particular examples from mathematics, from real mathematics, in order to support my arguments or to demonstrate my philosophical ideas or to consider some case studies and try to draw some philosophical consequences from these case studies. So I am thinking about the third paper, which is a methodology of case studies in philosophy of mathematics. And therefore, during my lectures, I will concentrate on these three issues and kind of think through the methodology I am using in this research. So I'm looking for your advice, for your feedback. What do you think? How I'm using these case studies? Is it an efficient way of using case studies? Okay. So what you may learn from my course, guys, I think, well, first of all, you can use my research as a template. Kind of a starting point for your research in terms of how case studies in philosophy can be done. Yes. Then the kind of when you go down in terms of levels of abstraction, you can learn some philosophy of mathematics. Yes, because it's all about philosophy of mathematics. And when you go even down in terms of abstraction, you can also learn some recent mathematics, right? And I will try to explain these mathematics as clear as possible. Okay. So these are all the topics of the course. I think you know them. You saw them on the list already, and I think. Well, I want to present my papers and my research, but I have to give you some overview, some introduction, where these cases come from, where these questions come from, why I am doing this research and not the other research, why this research is important, as I think. So I have to give you some introduction. And today is an introductory lecture. So just to explain who I am, where I am in this map of philosophy of mathematics and what has been done so far. Yeah. So, what is philosophy of mathematics about? Main approaches and philosophy of mathematical practice. Main approaches. I think the first 2 points you may know already. You can read it online, but very little has been said about philosophy of mathematical practice. And today I'm going to introduce this area. It's relatively new, and so that you can know who are the people, what they are doing, and where I am in this map. Okay. By the way, do you understand me? My English? Okay. Can you hear me well? Good. So, what is philosophy of mathematics about? And this is a little bit of a naive view. People, when you ask people, what do you think what this could be, they usually say, well, it's about mathematics, of course. Yeah, what else? And the other people say, well, it's also about the questions which mathematicians don't have time to think of, or they think about them but they don't have time to write about them. Yes, because they are busy with mathematics. And I think sometimes it's kind of useful to look at these naive points of view, because There is some naive truth in them. As I will show you later, when you think what mathematics is about, is very often determines a philosophical approach in philosophy of mathematics. I will show you in a minute what I mean. So this is a kind of so what mathematics is about then? Yeah, this is an interesting question as well, and this is a number of naive views. Sometimes school children say give these answers when you ask them. So they say, well, mathematics is about measuring things in reality, yeah, calculating things we have, solving problems. Some people say it's about numbers, yeah, measuring everything. And some people say it's about formulas, yes. And then you can see that that's where formalism starts, for example, yeah, jumbling with symbols. Mathematics is about proofs. This is quite a common view. Very often you can find this view, and as you can see, it can be very strong paradigm in philosophy of mathematics. Mathematics is derivation of theorems from axioms. This is also quite a spread point of view, isn't it? Mathematics is about abstractions, of course. Yes, it's about abstract objects. Mathematics gives us foundations for truth and the standards of certainty. Yes, search for certainty, as you can find in Hilbert's program, for example, formalism. I don't know how much you know about philosophy of mathematics, but don't worry if you don't know something, because I will emphasize things we need to understand my course. And some people even say, well, ask these questions: is mathematics science or art? Yeah, this is a very interesting term, and that's where you can think about such issues as mathematical beauty, for example. Yeah, this is where mathematical aesthetics may start. So, but seriously, the subject of philosophy of mathematics is what we are doing. We are trying to draw some assumptions, think of foundations, some implications of mathematics, limitations of mathematical thinking. Philosophers can think of methodology and also the virtues of mathematics. For example, beauty, as I mentioned before. So the major parts in philosophy of mathematics, as any other philosophy, is metaphysics, of course, yeah. Then questions was what mathematical entities are, how do they exist, do they depend, do they not? Epistemology. Here I put the major questions. So the major questions correspond to the major parts. So metaphysics is thinking about the existence, realism, for example. Epistemology is about how we come to know mathematics. Do we discover mathematics, or do we construct mathematics, or something else? And aesthetics. Yeah. So. This is a long list of contemporary schools of thought in philosophy of mathematics. And so we need to know only some of them in just approximately. So Platonism, it starts from Plato, and empiricism is something opposite to Platonism in a sense. But straight at the beginning, I have to say that these isms, Platonism, formalism, they are, of course, imprecise classification of approaches. I mean, what really happened. There were some bright people with bright ideas, and they were raising important questions, interesting questions, and other people would follow them, discuss things. So that's how it happened in reality, right? And we use this classification only in order to make it kind of easier to structure our discussions. So please don't take it so strictly as it's on the list. And I ticked the approaches which are probably the most relevant for our research. I will talk about Platonism a little bit, formalism, structuralism is that mathematics is actually about structures. It's an interesting approach, of course. And for example, a structuralist can be a Platonist and can be an empiricist at the same time. Yeah, you understand that these things can merge and they can blur. But what is important for us is try to answer the questions, right? Give some relevant approaches to the problems. Embodied mind theories. This is quite an interesting direction in philosophy of mathematics, and maybe also maybe more psychology of mathematics. So these people think, well, we are not just mathematical minds, but we are mathematical minds in physical bodies, and our bodies have two hands, two eyes, and this kind of brain, and we have to survive in this world, and mathematics is kind of an extension of our survival program, right? Of course, one can say that eventually it has been developed into an art, maybe to some extent. But nevertheless, and I think it's a very interesting direction. But I think I would be interested also in research in terms of not just considering that the influence of our of our body and embodiment of our mind, and that we are functioning in this kind of space, which most of us see as Euclidean, three-dimensional, yes, kind of, we conceive ourselves as vertical, and we see things in terms of vertical and horizontal, yes. But also, look, we have these amazing technologies nowadays. We have internet, we have very developed computers, new computers, yeah. And so they are extensions of our arms, yeah. They are actually extensions of our bodies, in a sense. So nowadays, when we create mathematics not only with our minds, but also with these strong, powerful instruments. And this could be an interesting research in terms of, yeah, for a philosopher of mathematicians. So maybe some of you may be interested in this. So social constructivism and social realism is very close to this line, and these people also think that mathematics is done in a society. Yes, it's not done. It's not done by not just by individuals, but by groups of people, institutions, mathematicians. Mathematics is probably one of the most international parts of knowledge in our life, isn't it? So there is lots of influence from these social interactions perspective, how mathematicians actually talk to each other, and how they write the papers, everything. And there are much more approaches. I just put a couple of dots here, but there is a new kind of approach, philosophy of mathematical practice. It's a new branch in philosophy, and this is where my heart is, this is where I am, this is what I like to do. The idea is to look closer to mathematical practice, how it's really done in reality, and not how it should be done. So I will focus on this approach. Well, I think there is a good framework when you start talking about philosophy of mathematics, introduced by Paul Vinasarov and his dilemma. Probably most of you are familiar with this dilemma. It says it has two central premises. One is mathematical objects are abstract. Yes, of course, yeah, that's what we think. And they exist independently of our minds. This is a realistic premise. Yeah, let's say, well, yes, they are abstract objects. This is kind of an ontological premise, and the second one is epistemological premise. If abstract objects exist independently of our minds, they are abstract, but we have some mathematics, right? So it means we come to know these objects. How? Well, according to our causal theories of knowledge, we have to have some interaction with these objects, right? In order to know these objects. I mean, you came to this room, I see you, you put your names on the list. That's how we know each other, for example. Same with mathematical objects, we need some interaction with them, but how? We can't touch them, we can't see them because they are abstract. So, the causal interaction is impossible. Looks like. Therefore, the conclusion is, therefore, mathematical objects are either unknowable, because if we stick the causal concept of knowledge, we have no causal interaction with them, so we cannot know them, or they don't exist. So it's a dilemma with two horns, yeah. But if we keep one, we have this first part, they are not unknowable, or they don't exist. Is it clear? Yeah. So either or. Most of philosophers of mathematics start with this dilemma because it's really very challenging, and it concerns two central questions: what mathematical objects are and how we come to know them. And for most of philosophers, it's a framework. And right, let me go on because it's Bob Hale and Crispin Wright have written a paper, Binasarov Dilemma Revised in 2002, and they said, well, of course you have ontological commitments in terms of we have ontological commitments. It would be nice to know what mathematical objects are, their ontological status, what they are. Abstract. Do they exist independently of our mind, and what is it like? But of course, this question is very hard, and it looks like so far we didn't succeed so much in solving it. But some people say, why don't we start with an epistemological end and try to see what is it like to create mathematics, to come to know mathematical objects? And Bob Hale and Crispin Wright, they suggest that we can take a list of all these, long list of these approaches, yeah, which I showed you before, and we can divide all of them into intellectual and intuitional streams. Of course, again, it's not a strict separation of two lines, definitely they overlap, but that's how we can structure our research, right? Let me explain what it means. Intellectual and intuitional. So sometimes they also called static and dynamic by Silucci, mainstream and maverick, foundational and philosophy of mathematics. This is this is what I will probably stick to: foundational philosophy of mathematics, or intellectual and intuitional. What does it mean, intellectual? Well, some people think how we come to know abstract objects. Of course, by our minds, yeah, through logic, just thinking about things. So the mainstream, this approach includes three big foundational schools: logicism, formalism, and intuitionism. So, and the second half of the 20th century is neo-logicism, Platonism, like Gödel, for example, neo-formalism, neo-intuitionism, and fictionalism, and so on. So the main idea, we come to know abstract objects intellectually by logic, for logicism, for example. And one of the focuses of these programs was that mathematics is nothing but proof-producing enterprise. Mathematics is about proofs. Yeah, this is the central concept of mathematics. And what proofs are for these people? Proofs are logical derivations from the relevant axioms. And this is more about logicism. Formalists would say, well, proofs are formal derivations from self-evident truths, right? And intuitionists would say proofs are something you can construct from self-evident premises. So the focus of this approach was proofs producing, yeah. And proofs were considered as a string of lines, derivation from axioms to conclusions. Here are some more characteristics of this mainstream intellectual approach. So they were thinking more on ontological and metaphysical issues, what abstract objects are, yeah, how they exist, and less epistemology, although not always, yeah. Foundations. They were thinking, they were really focused on foundations, finding the foundations of mathematics. These foundations were rather static, so something which exists forever. Yeah, this is how mathematics should be. Proofs, as I said, they had quite few case studies. Yeah, they were really they were more like armchair philosophers, not so much like empirical data. They were focusing mostly on such areas of mathematics as set theory, arithmetic, not so much geometry, topology, not so much analysis, and pretty much neglecting visualizations. So these are kind of main characteristics. Of course, as I said, it's not always the case. Yeah. So, for example, if you take logicism, Rudolf Carnap introduced these two principles of logicism. The concept of mathematics can be derived from logical concepts through explicit definitions. The theorems of mathematics can be derived from logical axioms through purely logical deduction. That's what I said before. Quite a challenging program, right? If you look at mathematics, how rich it is. So Frege had this idea that arithmetic can be deduced to logic, and for example, natural numbers can be introduced by use of logic and a naive idea of a set. However, Bertrand Russell discovered that there are problems with Frege's approach, and there is Russell paradox. Well, you probably know about that. That if you take a set R of such axes that X belongs to itself, then R belongs to itself, but at the same, if and only if R doesn't belong to itself. Yeah. So, and there were many paradoxes later on, but well, and, this is a famous Albert Einstein saying that, well, logic will get you from A to B, but imagination will take you anywhere. And by the way, this is a screenshot from Facebook, Mathematics Today. So it's quite an interesting blog, actually, I think. Let me say a couple of words about how this intellectual approach treated visualizations and what was the attitude to the roles of visualizations in mathematics. Visualizations were considered as a flaw, a violation in mathematical rigor. So mathematics is a sample of certainty and rigor. It's precise, and everything has been written down in strict mathematical form. For example, if you look at Euclid's geometry and Euclid's proofs, they rely heavily on visualizations. So these would be considered as gaps in mathematical proofs, and not a rigor theory, not a rigor mathematical theory. A picturesque example of this kind of treating visualizations in mathematics was a completely picture-free textbook by Landau, Foundations of Analysis, by 1930, this famous book, with no single illustration, and it was a textbook for students. Right. So Maurer, a historian of mathematics, has this passage that illustrations would imply that geometric concepts were being used, and geometry and visualizations was Schmierl. If you know German, in German it means something like a lubricant, something like a facilitation for stupid students to get the idea. Yeah. So very tough, and so it's not only visualizations, but together with visualizations, a geometric approach would be considered as non-rigor, unfortunately. Yeah. So this is a photograph of Misha Gromov. Misha Gromov, one of the famous nowadays geometers, Russian geometer working in Paris and Princeton. And he has an Abel's Prize for revolutionary contribution in geometry. So I will talk about him later. And he solved really many long-standing algebraic problems, and other people using his geometric approach to algebra has solved many long-standing combinatorial problems. However, he's saying that an instinctive mistrust most algebraists feel towards geometry, which they regard as non-rigorous. So there is kind of inertia in mathematical thinking that it should be all about symbols, numbers, sets, algebra, but not geometry. Geometry is impure. Yeah, it's something like a violation of rigor. And this is actually happening nowadays. Yeah. Of course, I have to say that there are many important reasons for intellectual approach. It's not that everything they were doing was wrong, not at all. They really were dealing with very complicated problems, such as paradoxes of set theory, consistency and completeness of mathematics. For example, they were Gödel's incompleteness theorems, right? Non-Euclidean geometries, vagueness and vagueness of definitions, because and computational demand. If you look at historical works, Jeremy Gray, for example, in 2009, has a good volume explaining that at the end of 19th century, beginning of 20th century, if you open the textbooks, definitions were very vague. And of course, philosophers done a very good job in order to sort of clarify these conceptual settings in mathematics. And of course, it was industrial revolution and a big demand in solving precise, concrete problems, physical problems, mechanical problems, and mathematicians have had to develop algebra very rapidly to raise the level of calculability, let's say, yeah? So no one is blaming intellectual approach. Just the issue is, it was a little bit of an imbalance in philosophy of mathematics. And probably we could, nowadays, we could add something else which was missing at that time. So there was a lot of criticism, and David Corfield, my external examiner, came up, he has written a book, Real Mathematics, where he criticizes intellectual approach and tries to introduce the new program, more like intuitional approach. And I didn't say so far that intuitional approach means not only that we come to know everything through logic and formulas, but also there are more like things what people call intuition. I will tell more about it later. So he said that there is kind of a foundational filter in intellectual approach. So this very strong focus on foundations of mathematics sweeps out all the other important questions in mathematics. So he said, straight away from simple inductive considerations, it should strike us as implausible that mathematicians dealing with number, function, and space have produced nothing of philosophical significance in the past 70 years in view of their record over the previous 3 centuries. So he was saying that, well, if you look at current mathematics, it looks like all the great developments and discovery has been done before 20th century. So nowadays mathematicians, if they don't produce proofs, what are they doing actually? Looks like nothing, yeah? But it's not so, of course. So this was his idea about foundational filter. Foundational filter sweeps out everything, which is also probably important for the development of mathematics. It sweeps away. So mathematics is only about proofs and foundations. Right? Giuseppe Longo from École Normale Supérieure, he's saying, in fact, any slightly original proof requires the invention of new concepts and structures. The purely deductive component wouldn't follow. So indeed, if you want to prove an interesting theorem or find an interesting proof, first of all, you have to set your concepts, right? And this is also an important part of mathematics. But unfortunately, the intellectual approach doesn't really appreciate this. Yeah, they miss these important things. If you look at the Philosophia Mathematica, so David Corfield also pointed out that intellectual approach doesn't use many examples, and they are mostly from arithmetic and set theory. If you look at the several issues of Philosophia Mathematica, even nowadays, for example, 96, 2001, 6, 11, there are only 8 articles. There are 8 articles of logic, set theory, and category theory, and only 1 or 2 on geometry, probability, and analysis. Less than 1 article on algebra, and, for example, no topology examples at all. Why not? I think topology is one of the most powerful areas of mathematics today. And, Poincaré conjectures, so many striking results we've got for the recent 20 years, let's say. So the intuitional approach, David Corfield and others, they suggest, they developed kind of a program for philosophy of mathematical practice, and so they say we should focus on the following questions. Why are some mathematical entities important, natural and fruitful, while others are not? What counts for the connectivity of mathematics? How is it that concepts developed in one part of mathematics suddenly turn out to be connected to apparently unrelated concepts in other areas? This I will also show in the case studies later. So sometimes it's really striking that one of a sudden unconnected for the areas of mathematics have the same things in common, same structures, so they are tightly connected. It's a puzzle. It's kind of a mystery which we philosophers could try to approach. Why are computer proofs unable to provide the sort of understanding at which mathematicians aim? So, like four colors theorem proof. Yeah, it's just a computer said, yes, I went through all the cases, I calculated everything. We cannot really follow the calculations. What is the status of this proof? We don't understand it. Nobody does. So, what could be a strategy for develop better proofs in mathematics? What is the relationship between diagrammatic thinking and formal reasoning? Yeah, mathematicians use diagrams and then they print a paper, and sometimes there are no pictures in this paper. Why is it so? What comes first, a diagram or an argument? These kind of questions. So, just to recap what the intuitional approach is about, it's more about epistemic issues. They also think that foundations of mathematics are not really eternal things, unchanged. They may be dynamic, they may be changing with the development of mathematical thought. Not only proofs are a central issue in mathematics, but also other things like discovery, reasoning with images, explanation, understanding, fruitfulness. This approach, historically, this approach started with Maverick stream. For example, Lakatos, Davis, Hirsch, Klein, and others. And these people, they started with the skepticism about intellectual approach. For example, they were skeptical about that an absolute foundations of mathematics is the only answer to foundational questions, and that solely logical analysis of mathematics can explain mathematical thought and its development. The beginner of this, the founder of this movement was Imre Lakatos. There is a misspelling. His book Proofs and Refutation. He gives a heuristic approach to mathematics. So he's saying that yes, you start with a hypothesis and then you test your hypothesis, and sometimes you find some counterexamples. Sometimes it's right, but sometimes you find counterexamples, and then you have to deal with these counterexamples. So you may adjust your theory, or you can get some more premises. So it's more like mathematics is more like a narrative. You ask a question, then you refute you raise a hypothesis, suggest a hypothesis, then you refute it, and you raise another hypothesis. So it's like a narrative, not just theorem proof. And so he gave some basic rules in finding proofs and counterexamples to conjectures. And at the same time, he uses many interesting thought experiments. So he is famous thought experiments about rubber space, for example. So he's saying something. Well, imagine that your triangle is made of rubber, so you can stretch it. You cannot tear it, and cut it, but you can stretch it. What will happen to your hypothesis, for example? This is a very interesting book. I highly recommend you. And he called it like something like quasi-empiricism. So you have experiments in mathematics. You observe behavior of things, and some properties are really like physical properties. Coming back to the dilemma, the Nasser dilemma, I have to say more about epistemic approach of intellectual stream. Yes, as I said, logicists would say that it's through logic we come to know abstract mathematical objects. But there is another idea, such as mathematical intuition, and it starts with Plato and his idea, his world of ideas, eidesis, things which exist independently of our mind. They are abstract, they are ideas of things we see in reality, but they are eternal, ideal, and what we have in our life are just material emanations of these, or incarnations of these ideals. Okay? So mathematical objects are somewhere there. I'm not very precise about this, but I just don't have time to explain the details. Anyway, there is a Platonic heaven, a Platonic world of ideas where mathematical objects live. Yes, that's where they exist, and they exist independently of our mind. Let's take this premise as a rough approach to Plato. How we come to know them, and he has this allegory of the cave in his book, The Republic. So we are just like people in a cave, and what we see, we don't see what happens in the abstract worlds. We don't see ideas, we cannot touch them, yes, we have no contact with them. The only thing we see is the reflections, the shadows of them on the cave's walls. So of course they are heavily distorted. Yes. We can't see the ideals clearly. We only see some imperfect shadows of them, right? So he has in his dialogue Meno, he has a very interesting explanation how we come to know mathematics. The idea is that we have immortal souls, and we have endless reincarnations in new lives, but of course we don't discover mathematics, we don't invent mathematics, but we just recollect mathematical ideas from the previous lives. Yeah? And the material objects, because they have some shapes, because they come to us in sets, in numbers, yeah, they remind us about that mathematical knowledge which we used to have in the previous lives, right? So in his dialogue, he says, he asks a slave, a boy, who never had mathematical background, and he asked him to solve the problem. Given a square, how to build a double area square around it. And Socrates is asking questions, this slave boy, and slave boy is just answering yes, yes, it looks like this, yes. And together with Socrates, they create the argument how to do it. They solve the problem. So this is the proof for immortality of souls, but at the same time, this is Plato's approach to Binasarov dilemma. Yeah. This is how we come to know mathematical objects, by recollection. But and also it's called, sometimes it's called mathematical intuition. Yeah. Gödel, who typically is considered as a logicist, did believe in mathematical intuition, and he was saying that we have some kind of special mathematical intuition, special capacity, which let us perceive mathematical objects directly. There is a little bit like of a mysticism in this view. So he was saying, despite the remoteness from sense experience, so we can't really see mathematical objects, we do have something like perception also the object of set theory, as is seen from the fact that the axioms force themselves upon us as being true. I don't see any reason why we should have any less confidence in this kind of perception, for example, that is in mathematical intuition, than in sense perception. So, Gödel's idea was that mathematical intuition is something like perception, but it's a special capacity, and why don't we trust it? Well, I think we should have a break now, maybe 10 minutes break. Do you mind? Have some water, and I will start in 10 minutes. Okay, thank you.
Qualquer quando estiver abaixo.
Tudo bem?
Thanks for coming. Bonjour, ça va? So you give a lecture in this history of mathematics course. I would like
To the first students, simple. Years of the profile.
That's nice.